Section 2.4, Solving Multi-Step Inequalities. So this is kind of just a continuation of the last couple of sections, kind of putting it all together. In order to solve a multi-step inequality, we isolate the variable, ideally on the left side of the inequality, using the same steps as if it was an equation. Now, we try to get it on the left because then it's less likely we'll make a mistake when we're graphing our solution, but you can keep it on the right technically if you want. We're going to do it on the left in here just to make it easier for ourselves. Remember that when you're doing step one, anytime you multiply or divide both sides of the inequality by a negative number, you have to flip the inequality symbol. Less thans become greater thans become less thans. And then finally we're going to graph our solution set on a number line. Alright, so let's see some examples here. Alright, so here's the first problem. We're going to solve and graph this inequality. What I'd like you to do is pause the video, try to solve it. Don't worry about graphing yet. Make sure you can solve it first. And then come back and take a look and see how you did. Alright, let's see then. Alright, so we see that we should end up with x is less than negative 3. Just as a quick rundown of what we did here, we started with the distributive property, then combined my like terms on the right side of the inequality, trying to get the variables all over to the left, even though it's going to leave me with a negative x, that's okay. Then I move my constants to the right, and then because I divide each side by a negative, I flip the inequality, and I have x is less than negative 3. So now we need to graph that on a number line. So I'm just going to make a number line. Clearly the important point is at negative 3. Because it's just less than, I know I do an open circle, and less than will go to the left. So all of these values over here will work. So if I pick one of the values over here, something like about negative 5, I should be able to plug that in to my original inequality and make it true. So I'll show you that check here. And so when I plug in negative 5, the check shows that the left side of the inequality becomes negative 13, the right side becomes negative 15, and negative 13 is in fact greater than negative 15. It's a smaller negative, so it is greater. Alright, so there we go. Let's try another one. Alright, our next example here looks a little bit more complicated because we have fractions involved, but we're just going to approach it the exact same way and see what we can do. So, pause the video, try to solve it. Again, don't worry about the graphing yet. Make sure that we get our answer right first, and then come back and check your work. Alright, let's see how you did. Alright, so we should end up with x is greater than or equal to negative 25. I just missed my or equal to in there, but I put it in now. Just to run through what we did here, first tried to move the variables all to the left, and because 2/5 and 4/5 are fractions with common denominators, I can just subtract the numerators. So 2 minus 4 is negative 2, so negative 2/5 x. Move the constants to the right, and then in order to deal with this coefficient of x, which is a fraction, I just multiply by the reciprocal. And so multiply by 5 over 2. And I want to make sure that I get rid of the negative, so I multiply by a negative 5 over 2. Now, because I've multiplied by a negative on each side, I flip the inequality from a less than to a greater than, and I keep the or equal to. Then, on the right side, 10 times negative 5 over 2, treat 10 as 10 over 1, yet negative 50 over 2, which reduces to negative 25. And so now the number line is pretty straightforward from here. Here's negative 25. I need to have a closed circle because of the or equal to, and I'm going to the right. So the easiest thing to check here would be 0. It's always convenient to pick 0. And it's pretty quick to see the check here. We obviously pick 0 because it's such a convenient number. Multiplying by, even with the fractions, is really easy. 2/5 times 0 just is 0, 4/5 times 0 is 0. So I get negative 2 is less than or equal to 8, which is true. So this is in fact a solution to the inequality, so I've probably got this right here. And there you go. All right, so that's a couple of examples. Let's just look at two last special cases. So there are times when we solve an inequality, we actually end up with special cases, which we've had with equations. When we had infinitely many solutions or no solution. Now, with inequalities, because most inequalities have infinitely many solutions, we're not going to say that. We're going to say something a little bit different, but it's the same general idea. So take a minute, solve both of these inequalities, and then we'll come back and talk about what that means, how to interpret them, and how we could possibly graph our answers there. All right, so go ahead, pause the video, and solve each of these inequalities. All right, how'd you do? Okay, so hopefully what you found is that in each case, the variables on the two sides of the inequalities actually end up canceling out. And what we're left with is a statement of just comparing two numbers. And the first example, we have -8 is greater than 4, and second example, 5 is less than or equal to 9. Well, anytime that we have our variables canceling out, our statement is just either going to be true or false. And so we use that to determine which special case we have. Clearly, in our first example, -8 greater than 4, that's not true. That is a false statement. Meanwhile, 5 is less than or equal to 9. Yeah, it's not equal to, but it is less than. So that is a true statement. So now what conclusion do we draw? Well, not surprisingly, like with an equation, if we end up getting a false statement, we conclude no solution. This has no answer. There's no number I can put in for x that will make that inequality true. So it's kind of weird, but if I wanted to graph the solution on a number line, I could just put a number line, and maybe I label it as 0 so it's clear that there's a number, and I don't put anything up here. I'm just going to leave it blank. So it's kind of a silly thing to include. That's why we can just say no solution here. Meanwhile, if I have an inequality that gives me a true statement, it doesn't matter what I plug in for x. Anything will work. So what I want to say is that everything's a solution, all real numbers. And so I use this symbol here to show all real numbers. It's better than infinitely many solutions. X is greater than 2 has infinitely many solutions. This means everything. So if I kind of wanted to show what this would look like, here's my number line. I need to draw a line over everything, which is again kind of a silly way to do it, but I'm saying that everything should be included. Any number, if I plug it in, will make that inequality true. So for the special cases, we're typically going to leave our answer using these symbols or the words that go with them. Whether that's no solution for a false statement or all real numbers for a true statement. All right, and that pretty much sums it up. I think that's plenty of practice, and now you can do it on your own. Hope this is clear.